Your phone says turn left in 200 feet. GPS needs Einstein, not metaphorically. Skip the relativistic corrections, and your position can drift on the order of 10 kilometers in a single day. That is not a philosophy lecture. That is what uncorrected satellite time does to real navigation, aviation schedules, and military timing chains that never sleep. So the question is not whether relativity sounds poetic. It is how two opposite time shifts, a factory dial turned wrong on purpose, and a receiver still doing math after launch, keep your blue dot from walking off the road. Most of us carry a quiet picture of GPS that feels almost insultingly simple. Satellites broadcast time. Your phone listens. Distance becomes position. And somewhere in the back of the mind, Einstein is optional garnish. Either general relativity alone bends time enough, or special relativity alone handles the moving clocks. Or engineers solve the whole problem once in a factory and never had to think about it again. I believed something close to that. It is seductive, because part of it is true. Newtonian orbital mechanics still holds the satellites in place. Electromagnetic ranging on L-band still measures how far each signal traveled. Rubidium and cesium atomic standards still tick with stabilities often near 1 part in 10 to the 12th or 10 to the 13th. Relativity is not the entire machine, but treat clock synchronization as classical and the machine still lies to you in kilometers, not inches. And the myths are specific. Some explainers imply GPS works because of relativity alone. Some insist only general relativity matters, or only special relativity. Some claim satellites are factory-tuned once, so your phone never applies relativistic corrections again. Each version sounds confident. Each version breaks the moment you ask for numbers. Positioning is a stack, and the stack only works when every layer tells the truth at once. Here is the first payoff that breaks the simple story. At GPS altitude, gravity is weaker than at sea level. General relativity predicts satellite clocks run faster by roughly 45 microseconds per day. But the satellites are also moving near 3.9 kilometers per second. Special relativity predicts motion slows those clocks by roughly 7 microseconds per day. Opposite signs, not one cartoon arrow that says Einstein makes clocks fast. If you ignored both effects, the net drift relative to ground clocks is about 38 microseconds per day. 38 microseconds sounds like nothing, until you remember that navigation multiplies timing error by the speed of light. If that combined steady gravitational plus motion offset stayed uncorrected, timing error stacks into roughly 11.4 kilometers of light travel distance in one day. So when you hear 10 kilometers wrong every day, that is a mnemonic, not a physical law carved in stone. The evidence-based steady offset model lands closer to 11.5 kilometers per day. 13.7 kilometers belongs to the gravity-only piece before the velocity correction subtracts from it. And if only one relativity were responsible, you could not explain why engineers pre-tuned the oscillators before launch. Which raises the sharper question. If relativity were just a metaphor, you would not need a factory setting that specific. Why would you launch a clock that is wrong on Earth on purpose? Because the clock is not supposed to win a beauty contest on a lab bench. It is supposed to be right in motion, high up and far from the gravity well you live in. Walk into the satellite clock clean room mentally with me. The nominal reference everyone quotes is 10.23 megahertz. Before launch, engineers set the oscillator to about 10.22999999545 megahertz. That is a fractional offset of 446.47 parts in 10 to the 12th. They are not fixing relativity with a slogan. They are compensating the steady in-orbit clock rate offset so the satellite ticks at the correct rate once it is at altitude and speed. Think of it like shipping a wristwatch that runs slow on the ground because you know the airplane cabin will make it run fast. Except the cabin is 20,000 kilometers up, the speed is thousands of meters per second, and the mismatch is measured in parts per trillion. This is where history stops being hand-wavy. In 1977, the U.S. Navy's NTS-2 navigation technology satellite test measured an in-orbit clock rate about 442.5 times 10 to the minus 12th faster than ground clocks. The combined relativistic prediction, gravity minus motion, was about 446.5 times 10 to the minus 12th. Within experimental uncertainty, the measurement matched the prediction. That is validation history, not a description of today's roughly 31 operational satellites or their mix of rubidium and cesium standards. But it mattered because it turned space-time arithmetic into a number you could log before the full NAVSTAR constellation even finished launching. Rewind 6 years. In 1971, the Hafele Keating experiment flew cesium clocks on commercial aircraft. Eastbound and westbound routes traced predicted gravitational and velocity time shifts on a world map. Portable atoms, not orbital ones, but the same fight between gravity and motion written into elapsed time. By 1995, the U.S. Air Force declared GPS fully operational for the constellation, and in 2003, Neil Ashby documented the relativistic clock design and corrections in Living Reviews in Relativity, giving later engineers a canonical map of what must be applied and when. That paper matters because it separates what is baked into the satellite oscillator from what must still be computed as geometry changes. If you only tell the NTS-2 story, you risk implying a single dramatic test ended the argument. Modern GPS still lives in maintenance. Uploads, monitoring, clock aging, empirically validated models updated as needed. So yes, factory tuning addresses the steady offset, but that is not the end of the pipeline. Meanwhile, the ranging side of GPS never went away. Your phone still measures electromagnetic time of flight on L-band, converts delay into distance with the speed of light, and intersects spheres the way classical navigation always has. Relativity enters as clock synchronization inside that chain, not as a replacement for Newtonian orbits or radio ranging. Without that split, you cannot explain why a satellite leaves the factory deliberately slow on the ground, yet still needs a receiver that recomputes geometry every second. Shift from the clean room to a moving Earth. Factory tuning fixes the clocks, not GPS. Your handset still applies relativistic corrections beyond the satellite's factory frequency offset. The Earth rotates under the constellation. That rotation introduces path-dependent timing shifts at the hundreds of nanosecond scale, depending on geometry. Call it the Sagnac effect. Real orbits are not perfect circles either. For an eccentricity around 0.01, the periodic relativistic orbit correction can reach about 23 nanoseconds. Smaller eccentricities produce smaller amplitudes. Wait, what? You pre-tune the satellite and the receiver still chases nanoseconds from geometry? That distinction is the guardrail against the myth that relativity was solved once on an assembly line and then forgotten. Steady satellite clock rate offset is one correction class. Geometry-dependent fixes are another. Collapse them, and you misread how much work the receiver does every second. If the receiver ignored Earth's rotation, timing would inherit the planet's spin as fake delay. Every GPS satellite carries its own rubidium or cesium standard, yet the constellation must act like one synchronized clock in the sky. Even after the steady 38 microsecond per day offset is handled, geometry keeps moving. Earth spins, orbits are slightly elliptical, and your receiver location changes which path the signal took. That is why GPS is not a museum piece about 1977. Meanwhile, the rest of GPS still has to be GPS. Trilateration still needs honest ranges. Honest ranges still need synchronized clocks. Synchronized clocks still need both special and general relativistic terms, pre-launch tuning, and live geometry corrections working together. Relativity is essential for clock synchronization in this stack. It is not the only reason a constellation can turn time of flight into a corner you can trust. Picture trilateration without preaching. Each satellite broadcasts a timestamp tied to its onboard clock.
Your receiver measures how long the signal took to arrive, converts that delay into a range using the speed of light, and draws a sphere around each satellite. If the clocks disagree, the spheres do not meet cleanly. If the clocks disagree by tens of microseconds, the intersection does not merely wobble, it walks across the city. That is why the opposite sign relativity split is not trivia for physics class. It is how engineers size a factory mistake on purpose and still leave room for receiver-side fixes when the Earth rotates and orbits breathe. Back to the street-level stakes. About 31 operational satellites, as of the reference date, maintain a web of synchronized time in space. Each carries atomic standards stable enough that a part per trillion mistake would echo through pseudo-orange math at the speed of light. Ignore the net 38 microsecond per day drift, and tomorrow morning's fix is not merely fuzzy. It is wrong in the way that matters to pilots, truckers, and soldiers who cannot afford a philosophical debate about Einstein. The popular 10-kilometer story is close enough to scare you. The combined steady offset story is closer to about 11.5 kilometers per day. 13.7 is the gravity-only contribution before the velocity correction. And that gap between rounded story, gravity-only shorthand, and modeled net offset is worth keeping straight. It is the difference between a headline that fits a thumbnail and a specification that has to fly an approach in fog. If you remember only one number, remember 38 microseconds per day net before corrections. If you remember only one object, remember the dial that looks mistyped at 10.22999999545 MHz. And the 1977 NTS-2 plot was never the end of the job. Operational GPS keeps applying empirically validated correction models, upload adjustments, and aging clock care. That is engineering maintenance, not a one-off stunt that proved Einstein and retired. Global navigation, aviation, military timing, and billions of daily routes depend on correcting microseconds predicted by theories most people never think about when they tap navigate. The stakes are not abstract prestige for a dead physicist. The stakes are synchronized time you can trade for distance without driving into a field. So when someone says GPS proves Einstein was right, the careful version is narrower. The clocks measurably drift in the directions relativity predicts. Engineers compensate with specified offsets and live corrections, and the constellation keeps working because the pipeline never stops doing the math. Return to the dial that looks like a typo. 10.22999999545 MHz is the physical reminder that spacetime is not decoration. Gravity adds time, speed subtracts it. Factory tuning and receiver geometry corrections fight over the leftovers so your map does not migrate across the city while you stand still. GPS does not work because relativity alone whispers coordinates into your phone. It works because a multi-layer stack measures distance, synchronizes time, and applies Einstein's corrections where microseconds still behave like distance. Wrong on Earth on purpose, right in orbit by design, still corrected on the ground because the planet will not sit still. Your turn left instruction only feels boring because engineers already fought the microsecond war for you. On No Science, we follow the evidence, the instruments, and the experiments that change what we think we know. Which GPS relativity fix would you trust on a foggy approach first? The factory oscillator offset at 10.22999999545 MHz, or the receiver still applying Sagnac and eccentric-orbit corrections after launch? Thanks for watching. See you next time.